Hello everyone, welcome to this next video on field theory. In this video we are going to see example which is the set of integers modulo 5, right? So what is this set? So first of all let us define this set. In this set we have two operations. What are those? For field these are addition modulo 5 and multiplication modulo 5. These two operations are there. This is known as addition modulo 5 mod 5 and this is known as multiplication mod 5, right? So here we are given the set of integers, right, and we are given mod 5. So particularly the set would be, for addition it would be the set consisting of 0 1 2 3 and 4, and here in multiplication the 0 is not considered, so the set becomes 1 2 3 and 4, right? And how these operations are applied? They are applied as if, basically to see whether this z5 together with these two operations is a field or not. What we need to check, we firstly what we do, we create two tables, addition mod 5 table and multiplication mod 5 table, right? So we need to see how these tables are constructed. So we just list the numbers here horizontally and here vertically, right, for addition mod 5. So we need to fill up this table. How can we do that? For that we need to see how this operation operates on every two elements. That is, we need to check this is the entry for A, this is the entry for B. So we need to check what is A mod 5 addition mod 5B, what is this quantity for every number over listed over here, right? So this would be different from the normal addition. That's why we require these kind of tables, right? So how this operation works? This operation works like we can add these two numbers A plus B, whatever is the number C, then we divide this number by 5. Here it is given mod 5, so we divide it by 5. Whatever is the remainder, that is our answer, right? So let us see how this works. So I have 0 plus 0. So the 0 plus 0 is 0. When I divide 0 by 5, the remainder would be 5, right? In a similar manner, we can fill up this table. For example, I have 4 and 4. If I add these to 4 plus 4, that would be 8. And then when I divide 8 by 5, I'll obtain this, right? I can write 8 as this. So I obtain the remainder as 3. So the answer here would be 3. Likewise, if I have 2 and 4, what would be that? It would be 2 plus 4, that would be 6. And when I divide 6 by 5, I'll have 1 as the remainder. So that was it, right? 2 and 4, so it was 1. In a similar manner, we can complete this table. For multiplication table, what we are doing, we are simply taking two elements. Say A is my this column and B is my this row. Then I can multiply these two, whatever is the number here. Then I will divide this number by 5 because we are calculating mod 5, and whatever is the remainder thereafter, that would be my answer, right? I'll fill that value over here. So for example, let us see an example. Suppose I have 3 and I have 2. So what is the quantity over here? 3 multiplied by 2, that would be 6. So C would be 6. Then when I divide 6 by 5, the remainder I obtain is 1. So here it would be 1. Moreover, let us see another example. 1 multiplied by 4, when I divide by 5, I obtain the remainder as 4, right? So 4 would be written as 5 into 0 plus 4, right? So 4 is the remainder. Likewise, you can complete the table. If you wanted to do it yourself, pause the video and then see whether you got the correct entries. I recommend you to do that. So let us see what is the table. So these are my values with the corresponding operations. Now we need to check whether the set this Z5 is a field or not. To check that, we will check that whether this is a group under this operation and this is a group under this operation. Moreover, does it satisfy the distributive property? So let us do that. This is very simple. What we need to do is, for the closure property, we take any two elements from here, from the given set, and then we apply this operator, this binary operation onto that, addition modulo 5, and then see whether that the answer, the remainder, is again in the set or not. That means it should be one among these 0, 1, 2, 3 and 4. So let us, from a quick look at this table, suggest that every number here is of the form 0, 1, 2, 3 and 4. Therefore, we can say that whenever we take any two elements from the set F and we apply addition mod 5 to it, the answer would again belongs to the set F. That is, it is among these numbers only. So the closure property here is satisfied. Similarly, in a similar way, we need to check the properties for multiplication mod 5. So if I take any two elements among 1, 2, 3, 4, and then I apply the operation of multiplication mod 5 onto these, the result would again be in F. That means the result should again be one among these 1, 2, 3 or 4. So from the table, these are your answers, right? You can see that each entry is either 1, 2, 3 or 4. Therefore, the closure property under multiplication mod 5 is valid. It is true, right? The next property is to show check the commutative property. What would be that under these two operations? It would be A mod addition modulo 5b should be equal to b addition modulo 5a, and for multiplication it should be A multiplication mod 5 b should be equal to b multiplication mod 5a, right? So if you take any two numbers here, then the reverse should also be true. So let us have a quick look. If I take a to be this number 3 and I take b to be this number 4, then what would be the what would be 3 addition modulo 5 4? It would be 2, right? This number 2. And now if I check the opposite, that is, if I take 4 first and then I take 3, what would be the result? The result would again be 2. So these two are same. Likewise, you can check for every number that this commutative property would surely hold. So the commutative property under this operation holds. Next, we'll check the commutative property under multiplication mod 5. So again, let me consider two numbers. Here, let me take 1 as the first number and then 3 as the second number. So what would be the result? The result is 3, right? Now, let me take 3 first and then 1. So what should be the result? It should be 3, and it is 3. So these two are the same, right? So from here you can say that this commutative property is valid under multiplication mod 5 too, right? So now let us move to the associative property. The next property is associative property. It says that if you take any three numbers from the set, then this property is true. Likewise, for multiplication, this property should be true. So let us check these for any two arbitrary numbers in the set. So let me take for addition, let me take 0, mod 5 and 1 and then 2, right? So 1 mod 5 2, what is that? 1 mod 5 2, it is 3. So let me write it here, 3. Then 0 addition mod 5 3, what is that? 0, so that is 3. So answer is 3 from the left hand side. From the right hand side, I first have to look up for 0 addition mod 5 1, and then I have to add these under mod 5 to 2. So 0 and 1 under addition, 0 and 1, that is 1, right? Then 1 addition mod 5 2, what is that? this 5 in the subscript of that symbol, right? So 1 mod 2, what is that? It is again 3, 1 mod 2. So this property is valid. These two are equal, so this property is satisfied for addition. Likewise, you can check this property for multiplication. Let us take again 1, then 2 and 3. So first let me do 2 mod 3. So 2 mod 3 is 1, right? So 1 addition mod 5, multiplication mod 5 1, and then 1 addition mod 5 1, that is equal to 1. So here I have 1. Likewise here you will first see 1 multiplication mod 5 2, and then you will see whatever the answer is with 3, right? So 1 mod 2, that would be 2. 1 mod 2 would be 2. Then 2 mod 3, what would be that? 2 mod 3, that is equal to 1. So that is, you get the same answer. So this property is also satisfied. So now next what I have to do, I have to look for an identity element. An identity element would be the one such that if I take A and I apply addition mod 5 with that number, I get the same number with which I have started, right? So can we find any number? So in this case, these was our A's, right? So for this 0, can you find any number such that I get 0? Yes, it is here. For 1, can you find any number for which it is equal to 1? Yes, it is here. For 2, can you find any number such that it is equal to 2 again? Yes, it is here. For 3, it is here, and for 4, it is here. So you see that these numbers correspond to the second entry, that is 0. So we can say that 0 is the identity in this case. So E1 is equal to 0. So this is the addition mod 5 identity, right? See, in the similar manner, we have to check this multiplication identity mod 5. What would be that? If I take any number A and then I operate multiplication mod 5 with some number E2, I should again get the same number. So let us see what is our E2 in this case. So if I again this column represents A. So if I have A, so what from where do I get this 1 again? Here. Then for 2 I get 2 again here. For 3 I get 3 again here, and for 4 I get 4 again here, right? So what is my multiplicative identity mod 5? It should be equal to 1. So E2 is equal to 1. So we have multiplicative mod 5 identity as equal, it is equal to 1. So these two properties are also correct, right? So now let us see, for every element, do we have inverse in the group or in the set? Let us move and see that. That means for every A, is there any number B? We need to check this B for every number A such that when I apply this operator of addition mod 5, I should obtain the identity E1, that is equal to 0, right? So let us see that. So for the number 0, what number again gives me 0? This is 0, right? Again for 1, we need to see which number here, which number should I multiply it with so that I obtain 0. So first of all, we obtain 0 with 0 mod 5, addition mod 5 0 is equal to 0, right? Then here I get 0 here, that is 1 addition mod 5 4 gives me 0, then 2 addition mod 5 3 gives me 0, and then 3 addition mod 5 2 gives me 0, and then 4 addition mod 5 1 gives me 0, right? So what are the inverses? 0 is the inverse of 0. Then what is the inverse of 1? It is equal to 4. What is the inverse of 2? The inverse of 2 is 3. Then what is the inverse of 3? The inverse of 3 is 2. And what is the inverse of 4? The inverse of 4 is 1. So we have inverses for all the elements. Therefore, the inverses exist in this case. Now, what is our E2? Our E2 is equal to 1. So let us see the inverses in this case. That means I am looking for some number b over here such that when I take multiplication mod 5 of these two numbers, I'll get the identity, which is equal to 1 in this case. So so what should we do? We should locate where this 1 is in this table, right? So 1, when I do mod 5, so I'll get 1. Mod 5 with 1, I'll get 1. When I do the mod 5 multiplication mod 5 of 2 with 3, I'll get 1. Then of 3, when I do it with 2, I'll get 1. And for the case of 4, I'll get it for 4. That means when I do 1 multiplication mod 5 1, I'll get 1. And if I do it 2 multiplication mod 5 3, that again I would get 1. If I do it 3 multiplication mod 5 2, I'll get 1. And if I do 4 multiplication mod 5 4, I'll get 1. That means 1 is the inverse of 1, 2 is the inverse of 3, 3 is the inverse of 2, 4 is the inverse of 4. So therefore we have inverses for every element in the field. So these two properties are also satisfied. Then we can say that this forms a group under addition mod 5, and this forms a group under multiplication mod 5. So these two properties are true. So next, the last property that we need to check is the distributive property. What would be that? It would be equal to this in the present case, right? So let us check the left hand side first. So the left hand side, let me take any three numbers. Let me take 1 here and 2 here and 3 here. So firstly we'll solve the brackets. So 2 addition mod 5 3. So we'll look this in this table. So 2 mod 3, what would be that? It is equal to 0. So here we'll write 0, and then we'll check in the multiplication table 1 mod 0. What would be that? 1 mod 0. There is no 0 here. So we cannot take this numbers because 0 is excluded from the group of the multiplication mod 5, right? We cannot take 0 over here, multiplication mod 5. So we can take any other number. Let me take 4 here, right? So let us see what we obtain then. So 2 addition mod 4. 2 addition mod 4, what is that? That is equal to 1, right? So that is equal to 1, this number. So let me write it here. And 1 multiplication mod 5 would be 1 again. Yes, that so the left hand side is equal to 1. Let us see the right hand side. The right hand side, we should check whether 1 multiplication mod 5 2, then addition mod 5 this 1 multiplication mod 5 4, whether this is also equal to 1 or not. So firstly we'll check what is 1 mod 2 in the multiplication table and 1 mod 4 in the multiplication table. So 1 mod 2 is 2 and 1 mod 4 is 4, right? So we have 2 here and we have 4 here. So we'll check 2 mod 4 in the addition table, right? So 2 mod 4 in the addition table is again equal to 1. So this 1 is equal to 1. So this would be true for every two numbers, right? 0 is the exception because in multiplicative group we cannot take 0. So that's why this distributive property is also true, right? So now this set integer mod 5, does it a field? Is it a field? Yes, this is a field. So we can say that it is a field. I'm sorry. This is a field, right? And why do we do all this? because here's a result corresponding to this, that for every prime number p, 5 is a prime number, right? So this set integer mod p, which is the set of integers mod p, it is a field. So this is the property, and you should remember that for every prime the set zp integers mod p is a field. That's it for the video. I'll see you in the next video. Thanks for watching.